So in the last class, so what is going on? Which topic we discussed in the last class? Hello? Hello? Hello?
Sir.
Am I audible?
Yes, sir.
Yeah, I'm asking you a question that last class, what topic I was discussed?
Actually, we have completed up to this flip-flop, sir. We have completed D flip-flop.
Okay, this T and JK also completed. JK also completed. Am I right?
Yes.
So this is the JK flip-flop with the case statements. Okay. JK with the case statements. Okay. Hello.
Case statements, sir.
Yeah.
Some delays, sir. We're getting some delays, sir.
Okay. So this is also completed, na?
No, sir. Up to D we have completed, sir.
Okay, this is the JK is also completed because JK from D already completed.
Yes, sir.
So the previous thing is this is T and JK fluffs. T, how can you generate the T? How can you implement the T fluff from the JK or D? From the excitation table, okay, you can see the T fluff is nothing but the next state is Q exclusive of T. So this is JK. See, this is the JK. This is the JK. You are implementing T from this JK. What to do? Generally, the problem with the JK is fine for all the cases except J is equal to K is equal to 1. This is the case. When J is equal to K is equal to 1, what happened means if present state is equal to 0, the next state becomes 1. If the present state is 1, next state is 0. So like this toggling is going on. It is not one-time toggling. This toggling is going on until the clock, whatever the clock you are applied here, is high. Clear? Hello?
Sir.
Yeah. So that is the one of the set.
People are waiting, sir.
Huh?
Allu wait చేస్తున్నారు సార్ మీరు అలో చేయలేదంట ఇంకా
ఎక్కడ
షమన్ ఆన్లైన్ లో సార్
ఆన్లైన్ లో వెయిటింగ్ లేదు ఆన్లైన్ లో మీరు ఇద్దరు ఉన్నారు అంతే
అతను గ్రూప్ లో మెసేజ్ చేశారు సార్ ఇప్పుడే
ఎవరు ఆన్లైన్ ఉంటే వెయిటింగ్ ఉంటే నాకు తెలుస్తుంది కదండి లేదు అంటున్నా
ఓకే సార్ ఓకే సార్
okay this toggling so means as long as the clock is available at the output the state is changing for the same inputs. I'm not changing the inputs, just I applied J and K 1 both are ones. So then I fed the clock. So at the output the next state is not stable. It is continuously toggling until as long as this clock period is high. This is the biggest setback of the JK. This is called the racing problem. For single input, the output should be stable. If the inputs keep on changing, the outputs maybe keep on changing. But here I am not changing the input, just I forward 1 to both J and K, and I am waiting at the output, but the output is not stable. It's continuously changing 0 1 0 1 0 1 like that, or 1 0 1 0 1 0 like that. This is called the racing problem. So that the JK need to modify So in two ways. The first thing is just you have to imagine that I said, I explained and I shouted in the just a minute before, whenever j is equal to k is equal to 1, the output is continuously toggling as long as the clock is, I said. You have to mention that point. So clock, suppose your flip-flop delay is 2 nanoseconds and clock is high for the 5 nanoseconds, then within the 5 nanoseconds of the clock period, your flip-flop may be toggled more than twice. Here, what is the cause means your clock period is higher than the delay of your flip-flop. So that if you can implement a clock whose width is less compared to the delay of the flip-flop, then you can avoid this situation. Understand?
Sir.
So generally in the industry, they will ask about design. In the design, mainly the clock is very important. So because the clock synchronization or clock, what is it one, analysis is mainly will influence the timing analysis of the designs. So that we have many circuits, many systems or many circuits in the chip, so that I think clock for each one clock may not be generated. So clock source may be one that should be forward, that should be fed to the all the digital circuits which are required. So my request is, while designing the clock, the designing of the clock hold and setup times are very, very important in the digital design concepts. Okay. So that is the one of the alternative. Another, anything is there means, I think it is a old traditional method, that is the JK bluff. You can take two JK bluffs and you can take one clock directly fed to the first bluff, and for the second it inverted clock is applied. This is the, I think this scheme is called what? Master slave JK. Am I right? Hello? Hello? Okay.
Yes,
master slave JK. So what is the wrong with the master slave JK means? I think it's a twice, two flip-flops you should take. It is a more complex and it occupies more space, and so it is against the our design, our VLSI concepts, against the VLSI concepts. Am I right? So anyhow, yeah, come. Sir, class, huh? Sir, good in fan. ఏది ఈ ఫ్యాన్స్ వద్దు, లైట్ వెయిట్ దట్టు వద్దా? Okay, where is others? Okay, understand? So anyhow, that's why I'm not going to the master slave JK. Just I'm talking about JK because of the setback, last case setback. So I tied both J and K, okay, and so and tied together and taken as the one input, that is T. The T means, you know, what is it one? Toggling, which means, so I think T may be 0 or 1. If 0, both J and K is equal to 0, then JK excitation table or characteristic table or truth table, you can take the same case. So that means no change will get. If J is equal to 1 and K is equal to 1, there is a lost case. That what actually disadvantage in the TP bluff, JK bluff, that you are taking as advantage for the what counter implementation. When J and K is equal to 1, then the lost case in the JK bluff truth table, you can write here. So means I think you, because of characteristic equation you got from the characteristic table, that when the next state is a function of the JK are the present states and Q is the present, JK are the inputs and Q is the present state. So that if you see the characteristic table, then you can understand that. So next state is a function of the present inputs and present state. That's it. Any doubt?
No, sir.
Yeah. ఎవరండి వెయిటింగ్ లో ఉన్నారంటున్నారు మీరు ఆన్లైన్ లోనా?
సార్ రమన్ అన్నారు సార్, గ్రూప్ లో మెసేజ్ చేశారు.
మరి మాకు రాలేదండి, ఇంకే క్లాస్కి వెళ్ళిపోయాడు. ఓకే, సో ఎనీహౌ, so I think JK is here. See, look at this one, JK Plough and TP Plough, what is that one, truth tables here. So earlier, see the diagrams. From the diagrams you can understand that yeah, so there is a T is implemented from JK and T is implemented from the D. So both D is implemented from the SR. Am I right? D is implemented from the SR. Okay, from D you can get T also. Simply that is the reason. That is Q is exclusive with T. Okay, for both the A and B figures, for the pictures whatever showing A and B, for them these are the codes. The first one is T from D, second one is okay JK from yeah D. Okay, got it?
Yes, sir.
Okay, the next one is, as I told you, yeah, so JK actually previous examples, what are the people have implemented, just we implemented based on the characteristic equation. Now our behavior of the circuit, behavior of the circuit. Okay, so now this is the another approach. You can design a Plough, JK Plough here. I took the example. I'm taken the example JK using of case statements, means using excitation table. So in the excitation table you have a some rows and columns. For each combination of something, the output is something, the next state is something. So based on the table you can implement your Ploughs. This is that approach where you can use the case multi-branching statements. Multi-branching statements. Here, see, everything is fine. I think you are good with the what is it? So all the declarations, port declarations and everything. So I think you are very fine, very comfortable. So now I'm talking about so always at the rate of positive clock. Of course, I'm taking a simple JK Plough without any clear and reset signals. So just I have one clock, that is positive clock. So I think whenever the positive edge clock is changing, the clock changes from 0 to 1. So the action will be performed. Whatever the statements in between the so case and case statement, I forgot one thing, that is begin and end also. You can write begin and end also, no problem. Otherwise case and case end case is also enough, nothing to worry. Of course this is also grouping kada, case and end case also grouping. Okay, case and end case are also used to grouping the statements. Okay, so I think case in bracket case expression is there. There are so many case alternatives, maybe JK both maybe 0 0 0 1 1 0 1 1. Whenever 0 0, I think from the truth table you can say next state and present state both are same, no change state, so that Q is equal to Q. Okay, so whenever 0 is equal to 1, the reset state, so Q is equal to 0. So 1 0 means set state, so that Q is equal to 1, and last state is, that is toggling state is, whenever both are 1 1, Q becomes complement. Yeah, and case and module. This is the, of course, yeah, this is one of the way, but this is I think this is more lines. It requires a little bit more lines than the earlier designs. So maybe you can choose whether you want to use either case statements or some other things. That is your choice. There is no restriction. But if you use the case statements, I think each and every case you can explain. You can directly, that means without confusion, you can say, you can write. That is the biggest advantage. That cross check is easy than that one, but it demands more lines than the the implementation using what behavior or what architecture. Got any doubts, please?
No, sir.
Yeah, okay. Yeah, so now so what is the difference between the PIPLOF and register? Register. So because you are PG students, about the registers. I think group of PIPLOFs are nothing but the registers. So for the sake of understanding, it is very simple to. So generally PIPLOF is, I told you the definition of PIPLOF is, it is a 1-bit in-bit storage element. 1-bit storage elements. Suppose if you want to store 2 bits, then you need the 2 PIPLOFs. If you want 3 bits, 3 PIPLOFs are needed. 5 need. 10 need. Like this, based on your requirement, how many number of bits, as the number of bits storing is increasing, the number of PIPLOFs requirement is also increasing. So that what they did is, the designers have done that a fixed amount of to store some fixed amount of information. So they connected some number of PIPLOFs together, so that you can say it's a register as the register. So as you know, the teacher is carrying the register, so which contains the people's attendance, students attendance. Okay, so there is attendance he is always posting, so that from that whenever you want he can open the register and he can you can say that what is our attendance and marks or everything. Like this register also, whatever you storing, that information will be as long as stable or so will be there until you change again. Okay, that is the register. Register means it is not permanently storage, but you can store some period of time, then you can override it. Okay, so that is that facility you have. So you may ask me that what is the difference between the register and memory? Yeah, of course, memory is also in analog circuit design or analog IC design. You can study about the SRAMs, DRAMs. These are the memories. What kind of difference between this? That is the analog design, the analog storage element. This is the digital storage element. That is the difference. You have to understand.
Yes.
Yeah. So I think that comes under the analog design. This comes under the digital design. So if you want, you can club them to make as a mixed design. Okay. Anyhow, register. Yeah. First, you have to, whenever you are going to define a register, whenever you are going to implement a register, first you have to decide how many bits you want to store, how many bits of register required. So 3 bits, 4 bits, 5 bits, 8 bits, 10 bits, that depends on your requirement. Okay, here is a small code is there which represents the register of 8 bits. So this is the register, 8-bit register. See, this is the 8-bit register. 1 minute. Yeah, this is my 8-bit register. I have inputs. Yeah, this is the D input. And these are the outputs, Q. This size is 8 bits. And definitely clock is, I use the positive clock. And clear is there. And set is there. So I think this is the, so inside this box, you have 8 PIPLOFs. 8 PIPLOFs. So let us say D0 to D7. Okay, these 7 PIPLOFs are there. Okay, for them clock is given. The clock can be applied for them either sequentially or synchronously or asynchronously. That depends on you. Yeah. Yeah, synchronous or asynchronous, you can take, no problem. Okay, synchronously or asynchronously. Synchronous means all the clocks can be what? So triggered by the clock, all the flip-flops are fed with the same clock at the same time. Okay. Similarly, so you can have a each flip-flop has an input. Okay, like this, and each flip-flop has an output like this. Individually, how they are tying means you can connect, they can tie with the clock or with the what output. So means, so this flip-flop output Q may be connected to this flip-flop like this. You can that is one type of clock feeding technique. Another technique is clock can be directly given, and with some other what is it one logic, you can feed the Q to the other circuits, other flip-flops. That is the way. Okay. Yes, see, yeah, these things, this is the output, this is the input, everything is 8-bit, 8-bit, 8-bit. Of course, register output should be a register. Okay, in the behavioral modeling, and the inputs, other inputs are scalar inputs are clock, clear, set. Already the function of the clear and set. The function of the clear and set. Okay, so I'm taking that. So because of we have clock, clear, set, you can include them in the what? Always sensitivity list. In the sensitivity list, positive edge clock is there, negative edge of the clear is there, negative edge of the set is there. Okay, so there underscore means bar generally here. Or you can write, if you're not interested, if you are confusing, then you can write CLRB, SCTB, clear bar and set bar. Okay, so we have three sensitivity parameters, sensitivity signals, clock and clear and bar and set bar. Okay, if anything out of these three signals, any signal changes, definitely you should enter into this loop. So if first you have to check clear, because there are clock, clear and set. Out of that, which one is having highest priority means clear is as highest priority. Clear has highest priority. So that if clear bar is equal to, clear bar, negation of clear bar. This is clear bar negation. So that means clear bar, if clear bar means 1, negation means 0. If this expression is 0, okay, then I think without second thought, we can make all the outputs 0. That means Q is equal to 0. All 8 outputs are 0. So if else if set, suppose if the first statement of if failed means that is not 0, that is 1. Clear bar is 1. Means there is no clearing action. Now check the set condition. Set condition. Okay. Else if set bar, negation of set bar means if it is a 1. No. If it is a 1. If it is a 1, set bar is there. Set bar means 0. Negation means 1. Okay. Then you have to write Q is equal to, because set all the outputs to 1. Okay. All outputs are make it 1. Else, suppose the clear is not working and set is not working. Okay. Then else Q is equal to D. Then your each Q, that means Q of 0 means first ripple of output is equal to D of 0. Q of 1 is D of 1. Q of 2 is D of 2. Like that, each ripple of output is what? Its input. So because I use D flip-flops here, so that D is so in the register construction, to implement the registers in the digital circuits, I think D is the best, because you are expecting what you are storing that should be in the, so out of all the flip-flops, D is suitable, because in the D table, characteristic table, if you check what D, whatever the next state is nothing but the D. The next state and the input D both are same. Due to that reason, the output is, you can say simply, output is same as the input. So that you are expecting from the register. If I store 1, that should be in the register. So I think else Q is equal to D and module. This is a 8-bit resistor. Clear? I think 1 minute. I think you have a doubt. You may get the doubt. What doubt means? Sir, internally I am using that. You are using the dp pluff. So where is the dp pluff in the code? As I told you, behavioral modeling. The behavioral modeling is implemented. Any DC circuit in the behavioral modeling based on the behavior or architecture or algorithm. So here I use the architecture. Okay, any doubt? Hello?
Yes, sir.
Huh? Hello?
Sir,
Any doubts? I'm asking. Do you have any doubt?
no, sir, till now it is clear, sir.
Okay. Yeah. Now the counter you can implement 4-bit counter, 5-bit counter. Yeah. What is the difference between the counter and register is nothing but register, whatever you store, that you will be, if you want to store any information, you can use the registers. So, but counter is not like that. Counter generally use it to any device to log out. Counter is generally used to count the binary sequence. So 0, 1, 2 events will count. Okay, so count maybe by default you can say count value is always incremented. If it is 0 previous, now it should be 1, then 2, then 3, then 4, like that. That should be incremented. That is called the counter. Okay, but register is not that. So counter need to always toggle. Okay, so that in the counter design, generally we use the TP pluff. D and T both are used to register implementation and counter implementation. See, here is a 4-bit counter. 4-bit counter means I think you need 4 flip flops. 4-bit. The number of bits and number of flip flops both should be same. But it can count to 2 power n number of bits. Numbers, binary numbers. 2 power n means here 2 power 4 is how much? 16. So this 4-bit counter can count 16 binary numbers. It may be from 0 to 15. Okay. So this is a counter. So I think it is a, what is that one? What I'm telling you. So without skipping off any state, it is counting 16 means. Suppose if you want to design 10-bit count, decade counter. Decade counter means what? It should be count 10 states only. At that time also you need 4 flip flops. But I told you 4 flip flops means you can count 16 states. But he is asking about 10 states. So remaining 6 states you should be skipped. Okay, that type of counters are called the modulus counters. Okay, module 2 counter, module 10 counter, because of 10 is a very vibrating word. So we said that is a decade counter. Otherwise, you can say mod 9 counter, mod 8 counter. So like that. Suppose if you want to count below the capacity of the counter, then comes under the what? Module counter. Okay. For example, yeah, you can design a counter. I think not a sequence. So you can skip. You can count 0. You may skip 1 and 2, and then you can count 3. You can skip 4 and 5, 6, 7, and you can count 8. Like that also you can implement. Any type of counter you can implement. Okay, the skipping of some sequence or regular sequence, continuous sequence, or maybe irregular sequences. You may count alternative sequence, alternate numbers in the sequence. Okay, the design approach is different. Okay, anyhow, the counters are used to count the binary numbers, binary sequence of numbers. Okay, generally the number of flip-flops requirement is based on the what number of how many bit of counter it is, and the counter may count the full count may be 2 power n number of what is that one bits. Okay, sometimes you can count less than its capacity, then that is called the modulus counters. So you may count continuous sequence or discontinuous sequence. Okay, if you yeah, that is the way you can implement the counters. Understand? Hello.
Sir,
Yeah.
దానికన్నా దాని క్యాపబిలిటీ కన్నా తక్కువ కౌంట్ చేస్తే
Modulus counters.
మోడ్యులస్ కౌంటర్స్.
Modulus. Mod 10 counter means it requires 4 flip-flops. 4 flip-flops means 2 power 4 is equal to 16. It can count. Its capacity is 16. But you are demanding to count only 10. Okay.
Okay.
So then you do some modification that will decide that will do in the design part. But this is called the modulus counter, mod 10 counter. This is mod 10. It counts the 10 states. The 10 states may be 0 to 9 or 1 to 10 or 2 to 11 or 1 skip 2 skip 3, like that also. So the way of counting is purely your choice. Purely your choice. Based on your choice, the design will start.
Okay, sir. Okay.
అదే చెప్తున్నాను కదా. సో ద స్కిప్పింగ్ మేబీ కంటిన్యూస్ స్కిప్పింగ్ ఉండొచ్చు, లేదంటే సో ఆల్టర్నేట్ స్కిప్పింగ్ ఉండొచ్చు. అదేనండి, 0 కౌంట్ చేస్తారు, 1 స్కిప్ చేస్తున్నారు అనుకోండి, 2 3 కౌంట్ చేసి 4 5 6 స్కిప్ చేయొచ్చు. ఏంటంటే కంటిన్యూస్ గా 0 to 9 కౌంట్ చేసి 10 to 15 స్కిప్ చేసేవచ్చు. That is easiest process. That is very easy. So whenever 10 comes, it should be clear, signal should be activated. Then everything will becomes 0, reset, clear. Then with the next clock, it starts from the beginning. అలా కాకుండా ఫస్ట్ ఒక 6 కౌంట్ స్కిప్ చేసి, అంటే 0 to 5 స్కిప్ చేసి 6 to స్టార్ట్ అయ్యి 15 చేయొచ్చు. ఆ ప్రాసెస్ కూడా ఈజీనే. అలా కాకుండా 1 2 3 కౌంట్ చేసి 4 5 6 స్కిప్ చేసి నెక్స్ట్ ఇంకొక 4 5 6 కౌంట్ చేసి 7 8 9 కౌంట్ చేసి స్కిప్ చేసి అప్ టు 15 మళ్ళీ కౌంట్ చేయొచ్చు. సో యూ హ్యావ్ ఎ full freedom. But so based on your requirement, some exercise should be on the paper. How the connections will be given from 1 flip-flop to 100 flip-flop, that is the purely design part. So after that, you can implement here. Okay, anyhow, 4-bit counter, see binary counter, module, counter, cube, clock and clear. So I think this my counter is 4-bit. Yeah, 4-bit counter. This is the Q. This is my Q, 4 bits. Okay, so this is the clock. This is the clear. CLR. See, outputs are 4 bits. They are registers also. Inputs are clock and clear. See, always because of we have 2 things here, clock and clear. Yeah, come to here. Pause edge clear, neg edge clock. He took this to reverse, negative edge clock. Okay, no problem. So you begin if clear. Clear is 1. Clear 1 means everything will be 0. Because I took clear directly, not clear bar. So that if the clear is activated, so output should be 0. All the 4 bits will be 0. Yes. Else, clear is not 1, it is 0. Then Q becomes incremented. Q is equal to Q plus 1, modulus 16. Okay. Then I think this is same thing. Both are same thing. Q is equal to Q plus 1. And if this statement is wrong, if this statement is true, then this is the final one. So that's one. I think the same thing, if you want to implement, it takes a lot of time. But now, because of, yeah, it's very simple. Okay, understand? Even
yes,
though I
sir.
told you, so DP plows and TP plows, but nothing will be used here. Nothing is used here because because in the behavioral model there is a lot of freedom, flexibility is there that you can write your design code with the use of what is it one? Yeah, so behavior, how the circuit needs to behave. Okay, or any simple algorithm with which the circuit is working. If this is not, then you can go that also, no problem. Okay, a lot of things is there. Okay, yeah. Now, please, any other things to discuss? Okay, we'll see later. Yeah. Second mid exam. What is the first mid portion? First two 1-2 modules. Second mid, third module. This is third, na?
Okay, sir.
Fourth module. Fourth module. Third module or fourth module? I forgot. Third module. Third module. So include third module, entire third module. There is a another subtopic is there. What is that one? Functions and system clocks, systems. Okay, that is there. That also included here. So what is the best time to conduct the exam? Hello?
Sir, until December 6th, it was occupied, like we have.
Up to 6th, December 6th?
We have occupied with mid, sir. I mean, December 3rd, we have analog, and in between 3rd to 6th, we have weekend, sir. And in 6th, we have RMIPR, sir. We can plan after 6th, sir, actually.
Why don't you plan before?
I think we don't have enough time to prepare MDHT.
Okay, so do one thing. You decide, okay, date, then inform me better. But my suggestion is before is better. So because 6th is what is the day? The 6th, December 6th is what is the day?
Tuesday, sir.
Tuesday. Then only Friday is there. Friday we have a class.
Yes, sir.
Okay, my exam is late. Okay, so we have some time so that you all 5, the Pandavas, should talk each other and tell me the answer. So you decide and give me.
Sure, sir.
Okay, then I think all are presented. I will post it in this number.